Okay, welcome to AP Calculus 4.3. This is derivatives of trigonometric functions. It's actually derivatives of inverse trigonometric functions in this case, but those are still trigonometric functions. I'm going to start trying to put out some problems that are from your homework. Hopefully you're going to use this to check your homework and not just to run through your homework. I'm actually going to put, I've got number 6 down here, but copied it wrong, but I'm going to go ahead and put that on a different page. I'm going to do this in bits. So the first section of this assignment asks us just to find the derivative of y with respect to the appropriate variable. So in this case, I'm going to be finding dy dx, and in this case, I'm hopefully going to be finding dy dt. Perhaps some of the biggest challenges we're going to have in this section are just arriving at the book's simplified answers, sometimes simplified to the eye of the beholder, but that's going to be good practice for us going forward, just working with our trigonometry, working with our algebra, and simplifying. So that's going to be our target, to get to some answers. I might talk about what might be acceptable at times, but when you get an answer and you check your book's answer, try to work through to that solution. Okay, so by this point, we should, at the very minimum, know how to derive each of these inverse trigonometric functions based on using just plain old sine. We'd set y equals sine inverse of x, then we'd get sine inverse of y equals x, and then go through some implicit differentiations. We have seen that, but you may be just cheat sheeting this for a bit until we get comfortable that we remember these. The good news is that sine inverse, cosine inverse are the same except opposites, and tangent, cotangent are the same except opposites, and secant, cosecant are the same except opposites. And in addition to that, plain old sine, plain old tangent, plain old secant are all positive, and cosine inverse, derivative cosine, or cosine inverse, cotangent inverse, and cosecant inverse are all 3 negative. So that might help with the memorization process. So might throw this back out here to kind of use this as a little cheat sheet for now, but we should be in the process of learning these. So we are first to find derivative y equals cosine inverse of 1 on x. So my cosine formula, in this case we're finding dy dx. My cosine inverse derivative is -1 over square root of 1 minus our argument squared. If it was just x, we'd be done with just plain old x squared here. If it's not just x, then we have a function of x in here, and we need to find the derivative of that. So I'm left, I'm not finding the derivative now, but I am going to rewrite this as x to the negative first, and we need to find that derivative. So equals, the derivative of x to the negative first is -1 times the -1, that's x, reduce the -1 by 1 to the negative second, all on square root 1 minus 1 on x squared when I square this. So that would become -1, oh, excuse me, that's +1 now, on, move the x squared to the bottom, x squared times square root of 1 minus 1 on x squared. And now, that is a pretty darn good answer, and if we were just finding the equation of tangent lines, might not even simplify beyond that, because we could just put a value in for x and get our derivative, get our slope, dy dx. But not too crazy about this little 1 minus 1 on x squared. So to clean that out, I've got these little x squareds in here. I could bring that, we don't typically do that, but much like if I had, say, sidebar here, if I had 5 times square root of 2, it would be weird to do, but I could make this square root of 25 times 2 if I wanted. And so I'm thinking about bringing this x squared in as a square root of x to the 4th. And I think that's going to clean up some of my issues here. So if I did that, going to steal a little bit of room here. I could make this 1 on. If I think of this as square root of x to the 4th and distribute that in here, check out what happens. I get a square root of x to the 4th times 1, that's square root of x to the 4th. X to the 4th times this is minus x squared. And you see I could actually, this is kind of weird, I'm playing a little ping pong here, little algebra ping pong, or radical ping pong. If I factor out an x squared, I can pull that out as a factor of x. So I could have just stolen one of these x's and put it in here as an x squared. And I get x square root of, if I factored out that x squared, I've got x squared minus 1. However, that, do we know what square root of x squared really equals? This x squared would be positive. When I square an x, and like, for instance, if I take negative 3, square it, take the square root of that, it comes out as positive 3. I need this to be a positive value. So that is how we would arrive at what our book is claiming is our final simplified answer. You could steal an x from here, but because x squared is positive, when we steal an x from here, we have to make the plain old x value be a positive value. If I stole x from here, I put it in as an x squared, and I get x squared minus 1. I could go there directly. So a little sneaky simplification there, and we'll see that from time to time. Hopefully we see it enough that we get comfortable with it. Okay, number 4. Here we are to find y equals sine inverse of 1 minus t. So of course this is dy dt. Sine inverse's derivative is 1 on square root of 1 minus the argument, or the baby function, squared. If this was x, I'd be done here, but now I have to treat the baby function, so I have to take 1 minus t's derivative, or find 1 minus t's derivative and multiply that on. So I've got dy dt equals, the derivative of negative t with respect to t is negative 1, making my numerator negative 1. On, if I go through there's some help, there's some reason to FOIL this. I think I'm going to have some good things happening. I'm scared to make sure I distribute that negative, so I'm going to leave the parentheses. If I FOIL 1 minus t times 1 minus t, I'm going to get a 1. I'm going to get a minus t and another minus t. And I'm going to get a plus t squared. For a potentially final answer, let's see, dy dx, negative 1 on square root of 1 minus 1, and then I get a plus 2t, and I get a minus t squared. Obviously that plus does not have to be here, especially since I have t's. It may be better not to put that in there and have it be confused as t. Okay, not too bad there. Let's take a look at number 6. Notice I've left a little bit more room for number 6. And the reason isn't just because I have a binomial. The reason is because right here I've got a product rule. And because of that, I'm going to treat, since I'm going to be finding the derivative of this square root, I think I'm just going to rewrite this with a radical rather than with an exponent rather than with a radical. So plus cosine inverse of s. I haven't started finding the derivative yet, so I don't say dy ds yet. Now I'm going to start that process. dy ds, first function times the second function. The second function is going to involve a chain rule. I want the just plain first function, s, times derivative of the second. That's 1/2. Leave the baby alone. Reduce 1/2 by 1, negative 1/2. Now treat the baby. Derivative of the baby function is negative 2s. That's just the first times derivative of the second, plus the derivative of first 1 times the just plain second. And I still have to find derivative cosine. Fortunately, it's just plain old s. So that is plus derivative of cosine of x is negative 1 on square root of 1 minus x squared. So we're taking derivative with respect to s now, so we just get 1 minus square root 1 minus s squared. Okay, I'm going to rewrite this, do some simplifying here. Here I've got an s ultimately times an s, but I've got a 1/2 times a negative 2, so that is negative s times s squared. That takes care of all of those. I'm going to put that on 1 minus s squared to the positive 1/2. If you want to make that square root, you could. I'm going to leave it like that for now. Plus 1 minus s squared to the 1/2. I'm going to leave a little space here. You'll see why in a second. Plus negative 1 on. I'm going to write this as 1 minus s squared to the 1/2, and I think you can see why I might do that. Now I have common denominators here. And clearly I can combine these, but it wouldn't be such a bad idea to introduce common denominators here by multiplying by 1 minus s squared to the 1/2 on itself. And then I've got common denominators everywhere. In addition to that, negative s squared plus, this would be a square root of something times square root of itself is just 1 minus s squared. I've got plus negative 1 or minus 1 all on. Now I'm going to go ahead and write this as square root of 1 minus s squared. So I end up with dy dx is negative s squared minus s squared minus 2s squared, 1 minus 1 cancel, all on square root of 1 minus s squared, or quantity 1 minus s squared to the negative 1/2. Okay, not too bad. 2 had some interesting reducing. Okay, number 8. Last in this section, dy dx is, I could make this to the negative first and do a chain rule, or I could quotient rule this. I'm actually going to quotient rule it. No real big deal here. If you want to make this sine to the negative first, or sine inverse, I should say, 2x to the negative first. Understand, this is not really sine to the negative first. This is sine inverse of. Sine to the negative first of theta is 1 on sine of theta. This is not 1 on sine of. So sine inverse of. So I want low d high, but the good news is low d high is 0. So it's whatever this low is times 0, 0, minus high, 1, times d low, we'll come back to that in a second, over the square of the thing below. I get this for my denominator, and now I need d low. Low d high was 0, minus high d low. So I want the derivative of sine inverse of 2x. Well, the derivative of sine inverse is 1 on square root of 1 minus the argument 2x all of it squared. All right, let's go through some simplifying here. I'm going to work horizontally. No, I'm not really crazy about that if I don't have to. I'm going to work vertically. Equals, let's see, I get negative 1 on square root of 1 minus 4x squared, all on sine negative 1 of 2x all squared. Or if I make this on 1 and flip and multiply, oh, you know what I didn't do? I didn't come up here when I took this. When did I take my derivative here? Low d high minus high d low. I needed to multiply this by 2. I still needed to treat the baby, didn't I? Glad I caught that. Negative 1 times 1 times 2, this is negative 2. My apologies there. So now if I flip and multiply, I end up with dy dx flip this, 1 times negative 2 over, got a mess, 1 minus 4x squared times sine inverse 2x squared. And I believe that is a back of the book answer. Okay, that wraps this video up. I will continue on in this assignment, as this portion of our assignment, the A section, should wrap up after we get through number 28 and jump up to number 35. So this is going to be put in sets. I don't know if I'm going to be able to get all of it, but hope that's helpful, and stay tuned.